Hello students, and welcome to our second video covering topics in section 3.2 of your textbook. In this video, we're going to talk a little bit more about bases and linear independence. Which means the 3 blue 1 brown video, amazing as it was, did not cover everything you need to know for this class. So I want to begin with theorem 3.2.7. This is a theorem that gives us a way of characterizing linear independence different from just the definition that we were given. So in this theorem, the claim is that vectors v1 to vm are linearly independent. The idea is that this is equivalent to saying that if a linear combination of those vectors equals 0, then that can only happen if the coefficients in that linear combination were all 0 to begin with. So, okay, the claim is that these two are saying the same thing. An equivalent way of stating this theorem is with the contrapositive, which is what your book does. So what your book states is that vectors v1 to vm are dependent, so opposite of linearly independent, they are dependent, that this is equivalent to saying that there exists some linear combination of the vectors that equals 0, where one of the coefficients, at least one of the coefficients, is not 0. So these are equivalent, but let me tell you right now, this first one is the one to remember. It's the one that gets used. We'll use it later on in the slides in a proof of another theorem. So if this first one's so much better, whoops, why does your book give you the second one? And the answer is because the second one is objectively easier to prove. And in fact, we are going to take the same cop-out your book does and prove this equivalent version. So let's do that. Let's prove this theorem that is handy in its own right, but and we'll see how handy it is also later. Okay, so when doing this proof, we've got this equivalent contrapositive version, and so we'll do each direction. This first direction, we're going to assume that the vectors v1 to vm are dependent, and then we'll show that we can write a linear combination of them that equals 0, where one of the coefficients is not 0. So, okay, let's start. Let's start with the antecedent here. Let's suppose we've got suppose we have some dependent vectors, v1 to vm. Then to say these are dependent is to say, I'm sorry, this is like such a mess of an equation. But to say these are dependent is to say that some vector in here, v sub I, is a linear combination of the other vectors. And so I just wrote it like this, v sub I is equal to c1 v sub 1 all the way up to ci minus 1 bi minus 1. And then this is just to show that v sub I is not on the right-hand side here. And plus ci sub 1 vi sub 1 all the way up to cm vm. Okay, so this is just a way of saying that these vectors are dependent. And now the trick is just, all right, let's subtract vi from both sides of this equation. Then we have 0 is a linear combination of the vectors v1 to vm. And we know for a fact that the coefficient on v sub I is going to be -1. And so there we go. We have found a way to write the vectors as a linear combination equaling 0, where at least one of the coefficients is non-zero. All right, that wasn't too bad. Let's check the other direction. So now we're going to assume that we can write this linear combination equaling 0, where at least one coefficient is non-zero. So we start there. And I'm going to say, all right, suppose that c sub I is the one that's not 0. Then now our trick is just to solve for v sub I. So, all right, let's move, c1 all the way up to c1 v1 all the way up to before here, and then everything after, move it all over to the right, and then divide through by ci. And again, this is kind of a mess, but we're just saying we've solved for vi, and that's got to be, all right, minus c1 over ci v1 all the way up to, all right, this is just to indicate that v sub I is not here on the right-hand side. So it goes all the way up to vi minus 1, skips over, goes to vi plus 1, all the way up to vm. So, okay, we can solve for vi. But that's just saying that vi is redundant because vi is now, we've written it as a linear combination of the other vectors. And this is just what it means to have the vectors be dependent, is that one of them is redundant. So we are done. All right, take that, Theorem 3.2.7. That wasn't too bad. All right, now a theorem that, yeah, I think is pretty cool and uses the theorem that we just proved. So here we've got Theorem 3.2.10, and this is a theorem that kind of gives us a way to characterize a basis. Oh, I'm about to sneeze. Oh, why not? Just talking about it made it go away. Awesome. Okay, so we've got, we're characterizing a basis here. So vectors v1 to vm form a basis of some subspace. The claim is that this is equivalent to saying that every vector in the subspace has a unique expression as a linear combination. So this ends up being really handy because we are going to use this fact that that if we have a basis, we have a unique representation a lot. In fact, in I think section 3.4, these coefficients are going to end up, we're going to call them actually the coordinates of v in this basis. So this definitely is going to come up more later. So just doing a little foreshadowing to build tension and suspense. But okay, let's prove this bad boy. Going from left to right, let's assume that our vectors form a basis of some subspace V, and then we'll show that each vector then has to have a unique expression as a linear combination. All right. So suppose that v1 to vm form a basis of V, and suppose that V is some vector in the subspace V. Well, since v1 to vm is a basis, we can write V as a linear combination of those vectors. And now we're saying, all right, suppose we have a different linear combination. Like, is this possible? Can we write V in this way with coefficient C1 to Cm, and also as a linear combination, but with coefficients D1 to Dm? Well, the trick here is to actually subtract this equation from this one. So if we subtract one equation from the other, then we get this. So the 0 here is from V subtracted from B. So those cancel, we get 0. And then on the right-hand side, all right, we're subtracting D1 V1 from C1 V1, gather like terms, factor out the V1. And okay, we get C1 minus D1 is our coefficient of V1, all the way up to Cm minus Dm is our coefficient for Vm. And now let's use theorem 3.2.7. So since these vectors are linearly independent, this equation is only true when the coefficients are 0. So this was what we just proved. But if all of these coefficients, C1 minus D1, Cm minus Dm, if all of the coefficients are 0, then that just means that C1 equals D1 and Cm equals Dm. And so, in fact, what we thought was a new way of writing our linear combination turned out it was the same way. You gave me some D1 V1 all the way up to DM VM, and nope, it was the same one I had to begin with. Nice try. Okay, so that's one direction taken care of. Now let's take care of the other direction. Let's suppose that we have some vector V, or sorry, not some vector. Let's suppose every vector in the subspace has a unique representation from vectors v1 to vm. Now let's show that vectors v1 to vm actually form a basis. So okay, let's start with our hypothesis. We're supposing each vector, every single one of them, can be uniquely expressed as a linear combination of these vectors. Let's just note right away that this already implies that the vectors v1 to vm span V. And remember, to be a basis, you need to span V and be linearly independent. So what's left to do is to show that v1 to vm are linearly independent. So, okay. every vector in V can be uniquely expressed as a linear combination, and 0 is in V. So this means 0 can be uniquely expressed as a linear combination of the vectors in V, or vectors v1 to vm. But we already know that we could, if we chose C1 to be 0, all the coefficients, if we chose C1 and all the coefficients to be 0, then that is the solution to this equation. But by the uniqueness of this expression up here, the uniqueness of this expression here means that C1 equaling 0 all the way up to Cm equaling 0, that's got to be the only solution to that equation. And so, by our theorem 3.2.7, this means that these vectors are, in fact, linearly independent as desired. Okay. Man, I like proofs. I don't know, really fun. I like being able to understand things. I hope you found that understandable. That would have been a nice note to end on, but I'm not done. All right, various characterizations of linear independence. This is where we're going to end. So something that I really like about your book is that it gives you these summary tables. It's been doing it at the end of several sections now. And it says, it gives you a summary of kind of a way of organizing some ideas that we've seen, because there are a lot of different concepts that are floating around, and some of them are interrelated. And so your book does a nice job of kind of gathering these so you can get them all in one place and see. And it's a really great test of your understanding to see if you can understand why all of these various notions are related. So here in the summary table, it's talking about linear independence. And so they say, all right, the following statements are all equivalent. These vectors are linearly independent. That's equivalent to saying, your book claims, that none of the vectors is redundant. And yeah, that's actually the definition of linear independence. So that's not surprising. This third one, also not surprising. It's kind of almost just a restatement of this number 2, where, okay, if redundant means that no vector is a linear combination of the preceding ones, well, that's not too much of a jump to see that actually that means that none of the vectors can be a linear combination of any of the other vectors in the list. So, okay, 2 and 3, these are really just like by definition characterizing linearly independent. This number 4, there's only the trivial relation among the vectors. What your book means by that is that this equation, C1v1 plus CMVM equals 0, that only has what's kind of known as a trivial solution, where all the coefficients are 0. Okay, so this is our 3.2.7 that we already proved. Now here, this is interesting. This is saying that to be linearly independent is equivalent to having, if you made a matrix with these vectors as the column vectors as the columns of the matrix, then if these are linearly independent, the kernel must be 0. And if the kernel is 0, then these must be linearly independent. So I'm going to let you think about why that's true, but it certainly has to do with this number 4. And then finally, we have another characterization based on kind of if you make a matrix out of the column vectors. This says, all right, linearly independent vectors is equivalent to having this matrix of the columns have full rank. And I will also say these conditions should seem familiar. Like, we've seen them before. Maybe when it comes to invertibility. So yeah, I'll let you think a little bit about this, and I will see you in the next video.